guess we can get started. I don't think we need to really review what we have been done last time, but because this is more or less disconnected, right? Because last class we are talking about how to do the partial equilibrium and general equilibrium, right? We prove what we call the existence of Lavoisian equilibrium, and we also show the first welfare theorem, right, which said Lavoisian equilibrium are operator efficient, right? Just maybe I think maybe good to draw a picture again to let you review what we have covered. The main thing about the general equilibrium can be summarized by the HF box, which you asked to draw in your assignment, right? So you can consider a guy is here, right? And a woman is here, right? And anything in this box, consider two good world. Anything in this box will be the feasible allocation, right? And outside is infeasible. And initially you have some allocation, right? You start with some allocation. I can start with E, right? And you can look at the indifference curve. Guy number one, and in different curves of the lady here, right? Everything in the middle will improve both of them, right? So anything above the black curve would be individual rational, right? Anything below the red curve will be individual rational for the woman, right? And and then you can also, without regard to this, right, you can also have a what we call the Pareto efficient frontier, where this point, right, will be the tangent, right, to the indifference curve of a guy and a woman, right? So this contains all the line. And the blue one is what we call the contract curve, right? This is the contract curve, right? And also this blue one will be the core, right? Will be the core. So the blue one, this one will be the core. And what is the in particular, if you look at from here, if you draw a particular line here, passing through this point, right? And this, right, the tangent to both will be the this will be the Lavoisian equilibrium. All right, so this is basically what we cover, right? And the question probably is, suppose we start with a this is the first welfare theorem, right? We start with an this first welfare theorem, right? It's just like any Lavoisian equilibrium is on this line, right? It's Pareto efficient, and any Pareto efficient can be implemented by the Lavoisian equilibrium, right? So this one, right? You can always find a line that is tangent to both, right? And then suppose you start here, you can always if you're able to freely transfer wealth among people, which is questionable, but if you can do that, you can move it to here or any point along this line, then you can jump to this Pareto efficient outcome, right? So that would be what we want to say. And I guess I don't really talk too much about that, but in particular, how this topic connects to what we talk about today is the general equilibrium actually failed to, in most cases, fail to take into account of uncertainty. In the sense that if you really want to talk about uncertainty, you need to talk about goods that sold in different states of the world. different contingents. Say if the rainy day, you got umbrella. In the different days, you got different you got different goods. Then because the world has too many uncertainty, right? In that case, actually you need too many goods. Okay, because you can always twist the model to say different state of the world, there's a one good, right? But then your model basically will expand a lot because there's too many uncertainty there. Okay, in that case, that's why general equilibrium actually don't work that well, right? And actually, that's the reason why we have people studying finance, right? But if the uncertainty can be solved efficiently, then there's no point of doing finance, right? Just like no one is studying the hawker center, looking at the wet market, right? Because we know pretty much it's a well-functioned market. We don't really worry about it. And we know the financial market is not really well-functioned because of uncertainty there. The certainty that is easy, right? Go to the market for vegetables. The agricultural product is, I mean, although there's some typical issue of uncertainty, but they're very limited one. And we don't have any problem, right? The perfect competition idea, we learn the general equilibrium works very well, right? But in the case, and you have uncertainty, doesn't work that well, okay? And here also, one thing we omit is also market power, right? And if one firm has, or several firms jointly have, can control the market, like the OPEC or other cartel, and that means that perfect competition doesn't make sense anyway, because the assumed price taker, or everything actually breaks down, right? The welfare, the welfare is a problem, right? Even in Hong Kong, right, or in China, we have a competition authority, right? They regulate the competition, right? People actually do not want to take the price as given, right? They all want to control the price. So even though Hong Kong is said to be one of the freest society in terms of economic freedom, right? And still, I mean, you still require competition authority, right? It's a recent thing. I mean, in US has been in competition authority like more than around 100 years, right? Hong Kong, I think less than 10 years. So, I mean, yeah, so that is I want to say here. So I want to, because I think we are deeply behind our schedule. So I hope to finish the uncertain today. I think it's hopeful. We have 57 slides. Should be okay. Hopefully, and then we can start game theory for the after this class. Okay. So so let's start it. I just changed the first slide before I come. I think if you download a little bit earlier, I just changed this single slide only, so everything the same. So the way to model uncertainty in the literature, there are many ways. There are too many. If you learn decision theories, then actually there are at least more than 10 to 20 ways to do it. So what we do is the very classical one. The simplest one is actually follow what you learned, the probability theory, right? You learn the classical probability, where you assume a kind of random experiment idea, okay? You would have face a bunch of outcomes. You don't know which one will realize, but you have complete knowledge what may realize, which means that there's no surprise. You can't be surprised by the outcome, okay? You may surprise that outcome comes about because it's a very unlikely thing comes out, but you actually know what are possible, what are not. And you are able to know the probability for each outcome. You can assign, okay? There's a clear probability. It may be objective, it may be subjective, doesn't really matter. There's a probability there. You can put a number there, okay? There's a fixed number assigned to each outcome, and this number add up to 1. So that is the framework we're using, okay? And I again emphasize this is one of the classical model uncertainty we're using, and there are many, and still this is the most useful one, okay, in terms of model uncertainty. Okay, this is just model uncertainty. I'm not talking about expectancy. This is just model uncertainty. Okay, even uncertainty with different way to model it. Okay, but let's focus on this one. Okay, the very classical one. And as we said, we follow the classical idea of probability, right? So that means that I assign probability to each one. So that means that the way we consider the easiest thing is to start with gamble-like probability, right? So there will be n possible outcome, and in our class, in this class, we focus on finite number of outcomes, okay? And if you, many of you know math very well, maybe better than me. I mean, you will notice when we talk about finite and infinite, there are many complicated things, okay? And things usually hold in finite, the property need not the same for continuous, not hold all the cases, okay? But if you make certain restriction, then actually things in finite actually will continue to hold in the continuous case. So most of the thing would still hold. So don't worry about it. I mean, even though we prove our utility theorem, we also use finiteness. Okay, but I think this is something I want to mention. Okay, so we would have a probability that assigned to each outcome. That means sum to 1. Okay, and that actually means this pi, the simplex of n-1. So that's the notation we learned in the last class is if there's probability, right? So that means that P1 up to Pn belong to the simplex of n-1. And when I write this notation, it actually means this guy. Okay? And in the two-dimensional one simplex, it's just this. In the one simplex, P1, P2, it's just 1 and 1. The one simplex will be just this triangle. Okay. Sorry, not this triangle, just the line. Sorry. So just this line here. Just this line here is because this is just P1 plus P2 equal to 1. Okay. And the 3 dimension, maybe I draw here. Easier to draw. Maybe I just draw the whiteboard here. So it's 3-dimensional, it will be like this. I mean, I hope you can bear with my drawing. Okay, I hope you can see this is a 3-dimensional graph. There's x1 here, x2 here, x3 is here. Okay, and what is the simplex here will be like this. Okay, and this is 1, this is 1, this is 1 is all the plane. This plane is the only the outermost one is the plane, which is the plane that P1 plus P2 plus P3 is 1, and this is the 2 simplex. Okay, so that is the notation we use. Why we use that? Just math people use this we call simplex thing, and then we just inherit from that. Okay, so that's nothing. It's a unique simplex. I mean, to be more exact, but because you can add up to 2 with me. But we focus on this idea. We omit the unit notation. Okay. So the idea of this is we can have a simple gamble. So each outcome would assign some probability. Okay. And the simplest case you can imagine example will be a coin tossing. Okay. You win $1 when you have a head, and $1 lose, it will have tail. For a fair coin, right, will be half probability you earn $1, half probability you earn minus $1. Okay. So here, and I write this actually, I have some assumption here. Okay. When I write this, you do notice that I only write down the outcomes in terms of the net outcome. Okay. And if I have to be careful, depends on what I care, I may have to think about this, right? Instead of $1, I should be doing the following, right? Instead of this, I should write what I already don't have, I have omega wealth, right? This should be something. Okay, this might be something, another way to write it. Omega or W is the wealth or current wealth. So which way you should use is depend on context and depend on how you think, right? And what is the appropriate model? Usually, it really depends on how you model the thing. Okay, but I can't say which one is more clear. But if you think about A as the outcome of the consumption, then you should model in this way, right? But sometimes it's just being lazy, we just model this in this way. So, because at the end of the day, why both way are right? Because at the end of the day, you were looking about, say, you evaluate later, you will see your utility of the outcome. You have a utility of outcome 1, okay? Then this outcome 1 can be just W plus 1. So I mean that is no even though say 1, there's no loss of generality to do it here. Okay, I mean because outcome 1 can actually mean the outcome actually end up with this number. So that's why I can write that in this way. Okay, but it have to be careful when you write this out. It doesn't mean that the current wealth is not important. Is it clear what I'm saying? So, and here do note that the A is an outcome, but I didn't mention what it is. Here's an abstract outcome. Okay, A1 can be n-dimensional good, as we do in the topic 1, or A1 can be a very complicated object. Okay, and A1 and A2 can be different objects, right? A1 may be the lottery, right? A1 may be a ticket to Japan, right? A2 may be a $5,000, right? A3 may be spending some time in a resort, right? So that can be completely different stuff. Okay, need not be the same. So it's very general idea. Okay, and that is what I'm saying. So another one we call usually is simple gamble. We just assign probability to outcomes. Okay, compound gamble is assigning probability to gamble. Okay, it's assigned probability to gamble, and the notation is very similar, but G1 up to GK is not outcome, but instead they're gamble. Okay, so you are making lottery over the gambles. Okay, so and again you have to satisfy the ideal probability. So some of the alphas must be 1. Okay, and an example would be the following. Okay, so the way to write it might be there's a game, there's 2-stage game. Okay, so first or simultaneously you toss a coin and roll a die. Okay, if it's a coin, give you a head, then you're going to win the money. If you're going to lose, you got a head. Okay, so like this, right? The thing is the first thing is you have the coin, you have head or tail. If head, then you win. Then you tail, you lose. Okay, you lose. Okay, and if you lose or win, what's the amount? Depend on the 4-size die is 1, 2, 3, 4. Okay, if you get a head and 1, you win $1. You head and 2, you got win $2. If you tail, you won, you lose $1, so and so forth. Okay, so and you can consider this as compound gamble in the sense that the first thing they do is do a win-loss. The second one is this guy. Okay, and but the other way to do it will be, okay, this is the two-step, right? So how I write that is you would be one way you do Gamble 1, you go gamble 2. Gamble 1 means win 1, 2, 3, 4, 5. Gamble 2 means lose 1, 2, 3, 4, 5. Okay, so it's lottery over this one. Okay. So if you write in this way, if you think, okay, how you think about this lottery, okay? And usually some people would think in this lottery, in this compound lottery, I can actually reduce to an 8-outcome simple lottery, right? Some people would think, and that is one of the axioms we'll use later. Why don't we just say will be 1, 2, 3, 4, -1, -2, -3, -4, right? And each with probability 1/8. Right? Can I do that? Actually, this one actually requires an axiom called independence or reduction. And you reduce, you don't really care how you get to the outcome. You forget about the process to get the outcome. You don't care about the final outcome. Okay? The process is not important. The ultimate goal is important. If you believe you behave in this way, okay, then you can do this reduction. And experiments have shown that actually that require a lot of rationality. Okay, in most cases it's okay, but in fact, marketing people would tell, right? Usually people would be, the way you frame the problem actually would change how they think about it. Okay, it's not, although this is, you should, to you, you should be indifferent between these two, right? You should be indifferent between these two. But in general, if depending on how you write, they may prefer one over the other. Okay, you think they're the same, right? Ultimately you get 1/8 probability to get each outcome, but in reality, actually surprisingly, actually it's not. One of the reasons, probably we'll mention later, probably we will not talk about this, but it's the way that people would overestimate the low probability outcome. Okay, very unlikely events, they will overestimate the probability. Okay, so if they look at this kind of thing, right? If they have a low probability here, okay, or low probability here, they will just do different calculation. Okay, just like some people think people buy lottery, right? Lottery is a very, very unlikely you win a lottery, right? Especially the first prize. Basically, you can think about if you buy over your life, right? Usually you don't make it, even you buy every time. Okay. And the same idea here, right? Just like small probability event, right? Maybe it's actually very small here, also, but not so small here. Then you will look things differently. Okay, but that is there are many things I can say, but I just leave it here. So the next thing is about outcomes, okay, and lottery. So we focus on finite number of outcomes, okay, and that means that we have a up to n is a fixed, okay, that's a fixed one. Well, n is very large, so in general it's not an issue. So I just have finite number of them, but I have a very large n, so it shouldn't be a big issue here, okay. And in that case, we can focus on the idea of lottery, okay, and lottery, because I fixed the number of outcome, I just need to mention the probability. Okay, so I call this lottery if this is a gamble, and I call compound lottery. I just mention probability. I just mention the probability. Do note that this the difference of gamble and lottery is not universal. It's the way I use it in my slide, because in some textbook, many textbooks, they use lottery and gamble interchangeably. Okay, they're the same thing. Okay, but the thing is, some people mention about probability only, and some people call the gamble or lottery is probability with the outcome. Okay, so it's kind of with different textbook they use a different one. So I think you win the Max Collier, Winston Green, they use just use the probability. Okay. And you look at the Rennie and Jack Hill, they will use the gamble. And I always find it very confusing because sometimes the lottery and gamble. So I just try to distinguish them a little bit. Then gamble include everything, the lottery just the probability. Okay. So I think it fit the English word, but it's not a universal thing. But when you fix the number of outcome, they're interchangeable, right? Because the outcome are implied already. Okay. So I just to make what I said is more clear, so I just call this lottery. Sometimes the book may call this gamble or lottery the same thing, but just a matter of notation. Okay. So from now on, we just focus on bunch of probabilities. Okay. Or a lottery over probability, a compound lottery. Okay. There's two ideas. Is that okay? Is that okay? Okay. So this is the example. You roll a die, okay, and it's a fair die, okay, and if you fair die, then the simple lottery will be 1/6, okay, and so if you're compound lottery, okay, you can have a following compound lottery. Half of the time you get P1, half of the time you get P2, okay. P1 will be a 6-phase die, so you have each outcome is 1/6. And the second die will be only 3-phase die. Yeah, so you only have 1, 2, 3. Okay. So 1/3, 1/3, 1/3. Okay. So that is the idea here. Okay. So that's how you write a compound lottery. Now, I guess now we understand how we model the setup. Okay. So there's difference between here when topic one we talk about the consumption good is n-dimensional thing, right? N-dimensional objects. And here we just generalize to the case where we have a probability distribution over the outcomes. Okay. So each outcome, although I say 1, 2, 3, 4, 5, maybe one is a n-dimensional vector. This may be a k-dimensional vector. This can be anything arbitrary. Okay. So I don't have any restriction on what they are. Although I put number here, okay. Number one actually can mean many different things. Okay. So there's no linear assigned number today. It can be a vector. Is that okay? The number just for the sake of convenience. Okay. So we talk about expected utility. As I hinted earlier, there are also many ways to evaluate how people make decisions over lottery or gamble. Okay, why people would like this gamble or not, right? Why people buy insurance? Why people do lottery? Why people go to Macau, right? And that is how can we model this? Okay, so one framework we're trying to do is a classical one. Is the what we call the expected utility, right? Probably if you learn the undergrad, that is actually invented by the von Neumann and Morgenstern, right? It's basically the or the genius of the mathematician at that time. So they invent how people behave. Okay, is maybe we review the outcome first. So what we are doing is a bunch of slides. I mean, there's some assumption. I'll let you go to the answer first. At the end, what we want is the following. We would have an expected utility, means a utility over a gamble. Okay. You would just can be decomposed that utility over each outcome weighted by its probability. So is you look at the lottery, you have many different outcomes. Okay. What you do is you reduce this problem, okay, to the certainty case. Look at each outcome, what's utility to that outcome, okay, and then weighted by the probability, okay, and this is the simplest framework you can imagine, right? And this framework is called expected utility. And we'll prove that what kind of axiom that lead to this outcome. We'll do a proof for this one. This is a short one, so don't worry. We just try to construct. I guess if I don't tell you this, then there's no different from undergrad. So we try to give you a short proof for that. And probably out of your head, immediately you would think how to generalize this guy. We will not talk about that, but just we briefly say here we take probability, it's linear probability, right? So the more general case is to make a function on this probability, okay? What I meant is instead of linear on P, you can have another function called maybe F or G, maybe F of PI, okay? So that would be one way to do it, okay? And I guess some of you in finance would know prospect theory, right? They would just, the probability, this probability, I mean, this one, this F, say PI, okay, 0 to 1, right? In this classical case, it's just a linear, right? For each value, you just map to this one. And if you, learn some prospect theory, right? You will say one of the main findings in psychology is people tend to unable to evaluate some decommon places, okay? So that means that when there's very unlikely, they still think they're likely, okay? When they are very likely, they actually don't think that's so something like that. Maybe something like that. I mean, so along is good line. People have a good idea when it's okay, but when go to end, it's not so good. Something like that. So you have yes. It just perceived. You can say G, any function f is just a function that f is a function that from 0 to 1 to 0 to 1. Just any function. And in the case of expected utility, generically they would be equal. But one way to generalize it is to this guy, right? It's just like when they have this one, they would do some probability weighting, okay? It's not perceived as it is. There's some adjustment. When low probability, they think it's higher. When high probability, they think it's less higher. I mean, there are many ways to do it, as I said. In experiment, especially people from marketing, and they will think they will know more. And finance also, and finance, they would study many prospect theory and on those. But anyway, for our class, we just focus on the very, very simple version, okay? Because of time, I mean, we are not, unable to cover so many things. Okay, so what we are trying to do is to give you axioms, okay? What axiom would lead to this thing, okay? Lead to this outcome. How people would think would lead to this one, okay? So why we do this is because all other model would do the same thing. You start with different axiom, you have different function. So that's why we have to learn how we arrive the basic one. And when you try to read other paper, then you will see how the logic goes on. Okay, of course, the proof may not be important, but you at least need to know what axioms would lead to what outcome, right? The proof itself probably is just like left to the theorists, right? But when you see which idea apply, then which axiom would fit your application, right? So no axiom would fit all the application. And it would be the case where you think in the case that apply to your application that you would just choose the axiom that meets your need, okay? And so let's start. And the axiom you will see is not too much different from what we have learned so far, okay? I think the first two would not be an issue, okay? At least for completeness, usually it's not, I mean, there's still paper talk about incomplete, but I think complete is usually is fine. Is I give you two lottery, okay? You can tell me which one you like better, or you cannot tell, they're the same, okay? I mean, they're indifferent to you, okay? Or one is better than the other, okay? Okay, so that is the first one. I think that should be fine. You can always do comparison. Pairwise, I only require pairwise comparison. I give you two things, you can compare. Okay, I don't need to tell me if I give you three things, can you compare? I don't need to ask you this question. Just any two, I can compare. Okay, and then how you can use this pairwise comparison to go to more than three actually is required transitivity, right? It's saying that if in a pairwise comparison, P to Q, you like P over Q. In Q and R, you like Q to R. It must be case that you P over R. So it's just from pairwise comparison to any say more than two, right? Because this is how you rank. You can rank a order over there. And I think I also mentioned in the topic one, right? This transitivity recently actually the model trying to remove the transitivity. Okay, the reason is being that again the human mind is unable to detect small difference. Okay, and just like bundle A and bundle B may be very similar, right? And bundle C and bundle D may be very similar. You can't tell the difference. But A and D you can tell the difference, right? So which is then in that case it's not transitive, right? So A and B are the same to you. B and C are similar. C and D are similar, but A and D are different. Is that clear? I mean, it's very often when even ladies go to the boutique store, clothing store, right? You try two different clothing, cannot tell. And two different, cannot tell. The other cannot tell, right? Yeah, the slight difference between each one, right? What usually my wife's doing is ask me, right? And I give the advice, right? And then okay, it's better than this one. Then break the tie, right? So yeah, so you would have some way to break the tie, right? But I mean, that actually exceeds certain intransitive preference. But anyway, these two I think is pretty much fine. Okay, and because with these two, okay, we can always have form a order of them. Okay, we can have the maximum and the minimum. Okay, the maximum may not be unique, but there will be a maximum and a minimum. Okay, the maximum minimum exists because there must be a bundle that is, according to this, is always better than others, right? Weakly better, and there's always a bundle weakly less. Okay, although it need not be unique. Okay, A1 and A2 can be the same. Okay, and AN minus 1 can be the same, or everything the same is fine. Okay, but we can have a natural order of them. So some notation, if probability 1 with AI, usually you just wear AI without the 1. So that's simple notation. Okay. Is that okay? Because this we can compare, so that's why you can always do this, and then you can just rearrange. Is that okay? It's okay. Now the continuity. Okay. The continuity actually, this one, if you look at the MWG or Redhill and Rennie, I think they use version 1 and version 3. Okay, and I think version 3 is very natural, right? Because continuity actually means upper set is closed. That actually we learned from topic 1, right? Just the indifference curve. There's the indifference curve is not is a closed one. It's a line. Okay, there's no dot there, right? And 1 is also a natural meaning of continuity, right? Actually, it means that if P is strictly better than R, okay, and there must exist some mix of them is same to anything in between. Okay, what does that mean? Maybe I don't know if a graph will work. Suppose we have P1 over P2, and actually remember it's in the simplex, right? So what it means is if P is here, I don't know, R is here, say, okay, and suppose there's some Q, okay, that means that you can always mix these two. There's some mixing these two will be indifferent to this guy, okay, and actually that is little bit more general than this because Q can be here. Okay, so that a little bit more than what this indifferent. So you would think if they're free bundle, they have strict order, it means that this one will be equivalent to you. You don't really matter. So you have an outcome. There's something better than that, something worse than that, and there must exist some probability you mixing the two is same as the middle one. The continuous in the sense continuous in term probability. So I can always adjust some probability, okay, so that you'll be indifferent between the two. Okay, so later you will see this is a very important part in the proof. Okay, this is actually the key part of the proof. Later you will see. Okay, this is the key part of the proof. Okay, just continuous in the probability. So there's some way of changing the probability, right? Because if you have the idea is like if alpha equal to 1, right? This lottery is better than Q, right? If alpha equal to 0, this lottery is worse than Q, right? So you must be changing the alpha continuously. At some point, you should be better, right? So the idea is like this, right? When alpha is 0, okay, it is worse, right? When alpha equal to 1, it is good, okay? And you keep moving, right? Then it must be some point here that is same, right? This is, you think this is something like the Q, like here, right? This is Q is here, right? If having 1, this is P, this is R, and you have some way mixing them, same as the Q, okay? So there's some along this line. Is that clear? Okay. So I think these two are pretty intuitive, okay? But I like the Rubinstein proposal in this definition, because this definition is exactly what we learned from topic 1. Okay, this topic 1 is the same. Remember the topic 1 idea. What's continuity topic 1? It's the following, right? If you still recall how do we define, just go back to topic 1. Okay, I have bundle number, bundle X, and bundle Y. What we said continuity is a neighborhood, okay? If X is preferred to Y, okay? There's some X prime, okay? X prime is the neighborhood of this. I use B, right? Some epsilon of X. And I have a Y prime. Y prime is in the some neighborhood of Y, and X prime is still better than Y prime. Okay, so actually means that X is strictly better than Y. Something nearby X also still strictly better than Y. Is that clear? Let me repeat the statement. We learned it before. X better than Y. Strictly, somewhere nearby X, there's something nearby X, must still strictly better than something nearby Y. Okay, you can make the something as small as you want, right? As long as And here the same idea. I have a same just P and Q, okay, some lottery. And there exists, okay, some neighborhood, okay, some lottery, still retain this continuity. Okay, so just very simple, right? I did like this lottery over the other one. I slightly change. There must exist some slight change in P, some slight change in Q. That thing still keep intact. Okay, it cannot be suddenly it's gone. Okay, I just require the exist some. Okay, I don't need all this. Just something there. Okay, it's very weak requirement. Okay, there's no case sudden change, right? Remember, continuity, right? One thing we fail continuity is lexicographic, right? Remember the example I make in the first class is the Shanghai marriage market, right? If you always said, I need a guy who has a house, who has high income, and who has a, I don't know, Shanghai Kuko, and so on and so forth, and you do it one by one, lexicographic, it's not continuous, right? It's slightly perturb the first condition, then actually everything fails, right? So that's why it's not a continuous one. And as I mentioned, a lot of cases we actually do lexicographic decision making. Okay, so this is continuous. Okay, so maybe I give this monotonicity a break because I think already over time. So I just give the last. This is very easy, so I think it's okay. Okay, so now I have an order of outcome, right? I can order A1 up to AN, okay? And in the case that exists a strict preference, okay? This did not exist, but suppose it exists, okay? Because everything is the same to you, right? If everything is the same to you, then this axiom has no meaning. But I mean, everything is the same, actually there's no uncertainty you need to mention, right? But at least there's some outcome that you think one is better than the other, okay? And a number that alpha bigger than beta, okay? So what here we say is something very simple. I think no one will disagree with this, is you prefer A over AJ, okay? And if you have higher probability to get a better outcome, okay, then a lower probability to get a better outcome, okay, you prefer this over this, right? Because you like AI more than AJ, alpha is bigger than beta, right? Unless you're crazy, I mean, you need to harm yourself. Otherwise, I think this is very natural, okay? Honestly, I think it's rather weak property, right? Because only two outcomes, right? And just a con that is in more of your favor, okay? And I guess the strong part is coming from this strict preference here, okay? And the thing is like you actually sometimes it's so small, actually you don't really care. So in that case, that probably you would not have the strict, because things are so small, you're not sensitive, because in your mind maybe say alpha is like 0.999, okay? So 0.999, beta is 0.99, then probably you just think the same. Okay, if you don't like this, maybe alpha is 0.99959, right? And this is 0.99949, then you actually don't think that, probably you think they're similar, right? So in that case, then this thing might fail, okay? Or this is like 0.01, maybe 0.001, and this may be 0.001, then probably you think they're similar as well, okay? The only thing is they fail is, I mean, I think it's always equal, I mean, at least equal, right? So it's usually defined, but the only thing it fails for monotonicity is that they're actually equal, okay? Because this is more like the strong monotone, right? It's not weak monotone. So I guess I should stop here, have a break a bit, and then we come back to talk about two more axioms, then we can start the proof. Okay, the proof will be, I think we just covered this only proof in this class. Okay. Yes, I can resume. Okay. So just to remind you the axiom we cover. So first, completeness. You can always compare the two. Transitivity. If A is P is better than Q, Q better than R, P better than R. So I think the two is just you familiarize very well. And continuity, okay, I use the second one, I think the easiest one, right? If there's a strict preference, nearby is also satisfied. So that is easiest to remember. And actually, you can do a proof. The proof, three of them are same, okay? And if you actually do economics, I mean, none of you do it, but if you ever happen to do it, actually it's a proof, three of them are same. Okay, but and the last one, the axiom we talk about is monotonicity, is saying that if you have two outcomes, one is better than the other, and you would prefer lottery that give higher probability to the better outcome. Okay, and the key point is strict, right? Strict preference. Okay, so which is I think that's the only thing that is only have a empirical content or experimental value is just this strict preference. Okay, it doesn't include the equal one. Okay. So the last one is related to what we call the last two is independence and reduction. Okay, and these two are the most controversial one. And actually, there are many experiments actually show that these two actually have a huge problem. You look at the psychology exercises. What it is the following. Okay, suppose we have a lottery. You prefer P over R. Okay, and what we have is if I add a redundant thing, okay, you mix over a redundant thing. This still the same. Okay, you have P over you like P over R. Okay, and then the same here. Okay, I mix R over this 1 minus R over Q. Okay, so just say you like P over Q, but now instead of asking P over Q, I just okay, I toss a coin. May be fair, may not be fair. If it is if it's a head, okay, I go as before. Okay, you can choose P and okay. First, I give you P and R. Okay, you choose P over R. Now it's the following. I ask the following. I toss a coin. Okay, if head, you still face P and R. If it's a tail, I always give you Q. Okay, and if you choose P over R, you should also still choose this one, right? Because I'm mixing certain thing, right? Independent means if I take away this, right, you should still get the same. Okay, and actually this one turned out to be people violate because they are unable to see P and Q when they combine and how things right actually the violate. Okay, so this one actually require some of rationality. So, okay. Okay. The main reason is being that, I mean, as I mentioned, I just erased, right? Because of small probability thing, right? If this preferred by this probably is due to some small probability thing there. We add there, the small probability may be gone. Okay, so things can be different. So that is why this axiom doesn't work in some time, right? Because you actually don't evaluate probability. Erase this linearly, right? So that's why this doesn't work. Okay. Is that okay with this one? So it will be the last one, the last axiom. Okay. The last axiom said the following. Okay, as just here. Okay, compound lottery. You can always you not care about actual lottery, but you just care about the final outcome. Okay, so for lottery like this, okay, remember P1 is lottery probability over n outcome, same as K. Okay, you have lottery over the lottery. You just only care about the probability. Okay, maybe this is a little bit not easy to see. Let me write that down. Okay, So put it this way. Okay. So suppose you have outcome, we just two outcome, A1 and A2. Okay. Two outcome there. And lottery one, okay, is the following. You have, say, half and half. Okay. And lottery two is saying, say, maybe 2/3 and 1/3. Okay. Now, so let's do the following. I have, say, 1/5 of A1, okay, and 4/5 of A2, okay. So how will you evaluate this lottery? Okay. So you only, if the same, okay. Sorry. Okay. So it's 1/5 of the time you get P1, 4/5 of time you get P2. Okay. So here we only care about the final result. Okay. So for you, it'll be same as the following. You just care about the final result. Okay. And how likely you get the A1, right? Is half, sorry, is 1/5 times half and 4/5 times 2/3. Right? Because 1/5 you get P1, 4/5 you get P2, so just this. So that's what this notation means. Okay? You just care about the ultimate outcome, okay? The probability of ultimate outcome. You don't care about how it comes, okay? You just care about the end process, okay? So that is what I mean. Is that clear? Okay. And okay, so basically it's what it is. Compound lottery can always simplify to pure lottery. Okay. And usually people, when you look at the textbook, they would combine the two. Okay. If you combine these two, actually means simple lottery can be written as compound lottery because you add something nonsense. Right? You can add something there, you still the same. You still keep intact. So that means that you can always change things, I mean, accordingly. I mean, some textbook, they would combine these two axioms and say, okay, the compound lottery and simple lottery are interchangeable, right? This axiom said you just can be compound to simple, and this actually said simple to compound. So that's why, because you can always add thing there. Right? So that is what it means. But anyway, this is axioms. I think the axiom I follow the Hill and Rennie textbook. So I guess I want to mention one thing is independence, okay, would imply monotonicity, okay? So independence is much stronger than monotonicity, okay? So this one looks like a trivial one, but indeed it includes this monotonicity, okay? But anyway, just a side note, I'm not going to prove it. In case you want to, you can look at it, but it's not particularly important, okay? So at the end, okay, we want to prove what we want to prove. At the beginning, we said utility over lottery is you can write it as a utility over a outcome that without probability, okay? The part without probability, and you just weight it by probability. Okay, let me repeat what we are doing, right? Expected said utility of a lottery or a gamble, right, will be just utility over each outcome of lottery multiplied by a probability, so weighted sum, okay, or weighted average if you like, okay. So one thing to mention is the difference between this utility function and what we cover in the first topic. In the first topic is a ordinal utility, which means utility just tell you which prefer to which one. Okay, the number by itself has no meaning. Okay, but here as a cardinal, okay, the difference would matter. Okay, if you multiply utility by 3, everything changes. You cannot just simply multiply. Okay, so that would be have some issue. And the second one is something also talk to some of you during the break is people actually have some utility and maximize. Okay, and that is not this theorem said. This theorem actually said the following: if you make decision following this axiom or this assumption, you would behave as if you have a utility and you maximize such utility. Okay, let me repeat the statement here. It's very important. Okay, this axiom is not saying people have a utility and they maximize utility. Okay, same as what we actually do in the first topic, right? There's no utility. We are not asserting people have utility, but rather we have a framework. If people following this, if we can estimate, or we know the utility, or then we can predict what they're doing, okay? Or we explain what they're doing, okay? And that is what they're trying to do, right? Or we can use another perspective. This is a normative theory, okay? It doesn't tell how people behave, but rather we tell how people should behave, right? If people are rational, you should do this, right? I mean, maybe not people actually doing this, but this is what they should do. If you think these are all things that is rational, is meaningful, is reasonable, and if you're going to do decision, right? This is what you should do, right? This is what you should assign, make the decision based on this. Okay, so this is the idea. Okay, so let's quickly do the proof. I can see many of you may not will not need the technique, but I think it's good to go over it a little bit and see how they prove the thing. Okay, so the first line is pretty trivial. Okay, it's proving a trivial case. This is I think is common in math. It's like you prove something trivial and then we go to less so trivial. Okay, the trivial case is if all outcomes are the same, okay, to you, which means that 1 is the best, n is the worst, right? If they are the same, okay, that means that A1 equal to A2 equal to A3, A4, A5 are the same to you, because A1 is already the best, right? So each one is the same, okay? Okay. And why I write this? Because we have said by definition A1 is right. So if they're indifferent, then everything is indifferent, right? So because A1 is at least as good as AN, then if they're the same, then everything is the same. Okay. And the second one, okay, by independence, okay, if 2 outcomes are the same, okay, you mix with another thing by independent the same. Okay, so just go back to the independence, right? So you start with a lottery with single outcome, okay? You mix with another outcome, the same thing, right? You can mix of any, you can keep this process, you can mix with all n outcome, right? So that means that all possible lottery would give you the same, okay? Because the way you mix is the same, any simple lottery. Now, and actually by reduction, any compound lottery the same as simple lottery. So we're done, right? Because all the simple lottery are the same. So that means that we have the expected utility by saying that all the utility actually give you 0. Okay. Expected utility also give you 0. So everything is 0. Because everything is indifferent to you. How can you represent this, right? Because the idea is, under this case, all lottery to be the same, okay? So how can you make this statement work, right? Your lottery, how can you make it to each outcome? The way to do it is make 0 everywhere, then it's still everywhere. Is that clear? So every outcome is 0, then the lottery will be 0, right? And you can see it doesn't work if you monotone transform, right? If you make it to 1, then you fail, right? If that's why cardinal utility, right? You cannot make U of out A is 1, right? You cannot make any positive number, then your model doesn't work, right? So it's cardinal. Okay, so that actually first thing we saw this is perfectly cardinal. Is that clear how we prove this first one? This is very trivial, but this highlight one important point that is non-trivial. This is cardinal, right? Now the second one is, I think it's more interesting, right? Is one is strictly better than the last one. Okay, the best one and the worst one will be strictly different. Okay. In that case, okay, as I said, we will use continuity. That is a key point of this. Is if for any outcome, look at the best and the worst. Okay. And by continuity, there exists a number that make you indifferent between the two. Right? There's a best and there's a here, right? The best and the worst. Anything you can put a number. Okay, it's continuous, right? There's some lot. There must exist some lottery, make you indifferent with your proposed outcome I and all lottery over the best and the worst. Okay, is that clear? So this idea is very similar to, if you recall, how we do in this framework, right? This is very similar idea. X1, X2. I have a outcome here. What I can do is do a 45-degree line, okay? And we know this is better than this guy. This is worse than this guy. By continuity, there must exist something in the middle that is indifferent, right? And this guy, in the ratio of this one is called utility, right? This number. This will be the same idea here. Okay, there. But here I just can go to the best and the worst by looking at each bundle, right? And here I need to reference to A1 and AN. Okay, so that's why in this proof the important part is finiteness. We only have the finite number of outcomes. When you have more than 5 infinite outcomes, then this construction doesn't work. You need a very sophisticated version. Okay, but we just focus on the finite one. Okay, and this number must be unique because of the monotone, right? Because you increase a little bit, that you increase a little bit of this, actually it's better, right? Okay, so the uniqueness comes from the monotonicity. Okay, and actually this guy is called utility. Okay, and we will normalize the case of the best is 1, the worst is 0. Okay, then this thing would work, right? Because 0, because by construction, right? This is when this is 1, this is 0, and this will be itself. Right? So this is by construction. Okay, so that means that I can always, for AI, I can write utility. Actually, turn out to be is the probability that you choose the best and you choose the worst. Okay. Now, so that means that every outcome can boil down to lottery over 2 outcomes. Okay. And what you're going to do is a simple lottery, right? It's by definition, it's a probability over A1 over AN, right? It's a P1, P2, P over PN. Okay. So that's why this, right? You can write it as A1, okay, will be a probability that this arise, and AN with this probability arise. Okay, is it clear? Let me write down here. Maybe this is easy to see. Okay, so A1 is actually 1 of A1 and 0 of AN, right? A2 will be U of A2, right? A1, 1 minus A2, AN, right? And AI, right, will be U of AI, A1. Okay, I'm not going to do the rest, okay? So any lottery, P, right, you can write as P1, right, P2 up to Pn, right? And that means what? Right? That means that is this, right? P of 1 will go to this guy, right? So that's why, how many A1 here? A1 is just P1 times 1, right? And then P2 times U A2, right? And P da 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 da, right? Pi U of AI, right? And AN the same. So this guy is this one. Because you only care about the final outcome to you, right? Because you can replace this is a compound lottery, right? To you, the same to you. So lottery over n outcome is a compound lottery over this too, right? To the same. So that's why you only care about the final outcome. So that's how you get this one, right? This is a probability you get A, right? Start from 1 is the probability 1 and 2 and 3 and so on and so forth. Is that clear? So I think this, yeah, your question. Yes. So because each outcome can be represented by A1 over AN. So lottery over the outcomes can also be represented by A1 because you only care about the final one, right? You indifferent between them is the same to you. So now the rest of step is rather simple, okay? Now we are trying to prove, okay, this. If this bigger than this, okay, it's the same as you write it as, because you can, as you said, we can represent it with A1 up to AN, right? A1 and AN, right? Just lottery over the best and the worst, and the same, right? And you have 2 outcomes, right? 2 outcomes. One is better than the other. If this probability is better than this probability, this is independence. Remember, independence is you have 2 outcomes. Just go back to here, in case you don't confuse. Here, you take your 2 outcomes, right? One better than the other, right? And this better than this if alpha better than beta, right? Is that clear? So it must be the case because you're comparing the best and the worst. This better than this if the probability of this bigger than this probability. So this is what is written here. Is that okay? Okay. So here comes to the final. Okay? No, we're done. No more. This is already done, right? Because this better than this is because the probability of, you can just look at the probability of this guy, right? Way over there, right? So in the construction of this is like this, right? Is you just need to tell me how you like this object, right? And this object is actually is a probability that of getting best and the worst, right? This is the construction. Okay. I mean, the proof is not complicated, as you can see, right? And of course, this is simple because we assume everything is finite, right? And you can imagine that if not finite, the thing would be complicated. Okay, but I mean, we are not mathematicians, right? So this, we know it holds for general case. Okay, we're happy with the special proof. Okay, Is that okay? Why, how I prove it? Okay. I hope that is clear. Is that okay? I mean, so don't worry. This is the only proof we cover in this class. Okay. No more proof. That's the end. Okay. I'm not going to prove anything further. Okay. You would have take me as given for the rest. Okay. If you want me to go to proof, I go to proof. But otherwise, I will just leave it as it is. Okay. For the remaining part, I think we will cover risk preference and lottery. Okay. And risk preference for those who learn finance, and probably that will be something you will do often, right? Because finance is basically people with this different risk preference, okay, are trading with each other, right? Or have different idea about the probability they trade with each other. Right? So, and it's important to study the risk preference. Okay. So basically, you will see the rest up to here are all terminology. Okay. We just define things. Okay. We just define, and here is we are trying to see how to compare people behavior. Okay. And why some people buy insurance, some people buy lottery. Okay. And we will try to explain this. Okay. Because people in front of the risk, they behave differently. Okay. So that's how we give some idea. Right. It's similar to idea we talk about normal good, inferior good, those kind of idea. Okay. A preference, we try to give certain property. Okay. And this one is more like subjective, right? Look at how people would think, right? Given the same lottery, how different people respond is the risk preference, right? You like this lottery over the other one, but the other guy do other way around, right? Given the same set lottery, how people behave, okay? And we can also compare lottery, okay? To you look at two lottery, okay? And can we say one lottery is always better than others, regardless of your preference? Okay. Can we say, regardless whether your risk preference, you will prefer one over the other? Okay. Actually, that later you see is called first order stochastic dominance. And the second one will be saying, if we assume risk aversion, okay, if one over the other, regardless of how risk averse you are, is actually later you see is called second order stochastic dominance. Okay. So it is more like we will compare kind of monotonicity. Okay. More better than less. Okay. This idea there. Okay. And how do we quantify this in this lottery framework? Okay. And the last two, probably I'll cover mean variance analysis. Okay. I mean, finance people would know very well about this one, but if you not do finance, then still have some a good way, because if you are not doing economics model, people in economics tend to not be very happy you focus on mean variance analysis. By mean variance analysis, you basically throw away the third order, fourth order. So you just care about mean variance. You don't care about kurtosis or skewness, and so on and so forth. Okay. Because always, from probability theory, right? So a random variable you can always describe by the first order moment, second order moment, third order moment, fifth, or up to infinite order, right? And mean variance analysis is just you forget about all this thing. To you, what matter to you, the lottery, is just the mean and variance. Okay, we'll give you some background why this is right. And a lot of paper actually focus on this. Okay? Especially in finance trading paper, they all mainly talk about mean variance. Okay, we'll just give you some reason why they are right and some application. Okay, so we'll be quick because that's basically definition. Nothing new to learn, no proof. There's some proof in the slide, but I'm not going to prove it. Okay, because the proof also very simple anyway. So I think you can read it by your own. Okay. So from now on, we will focus on a much simpler framework to get some concrete result, because that is as far as we can get if we still keep abstract outcome. So we focus on the simplest case is our outcome is a one-dimensional. Okay, it's just a real number. Okay, I guess it's rather simple, and we focus on the case where you can represent the outcome by a continuous random variable. Okay, it's L. Okay, do note that this is a big jump because before we talk about discrete, right? Now I just jump to continuous. Okay, you have to believe me that actually everything holds. Okay, so I'm not going to explain why it holds, and so just we jump and we assume there exists a big F and small f. Okay, some of you may say, okay, F always exists, but small f may not exist in some case, right? So that's why you look at the Mas-Colell Wisdom Green textbook. They use this when you do the differential. They take this guy. They don't put inside small f because of the existence of this, and also probably you learn math, and then big F is the better notation, right? It's another type of integration. But anyway, so and also include discrete case, this kind of writing. Okay, so if you change from the if you have continuous case, or discrete also true, is you would have to write expected utility, okay, in this form, right? But this is same as the summation xpx, okay, when discrete, right? This is same as that one, okay. But when you have continuous, then you have to integrate over this guy. But the same thing. If you, I think all of you would be happy with integration anyway. But in case you don't like it, like me, I don't really like it. Then we can just, in your mind, just transform this to this one. Just in your mind, just become a summation, and dx become px, then everything goes. Okay, because everything in this framework also holds for discrete. Okay, and because this integration can be interpreted generically by discrete. Okay. Anyway, so I think I follow the Mas-Colell textbook. I use the small u for utility for an outcome, and big U will be expected utility. Okay, big U over the L. Okay, so okay, over L, you can think about lottery. Okay? A number, just a number. Okay. So the first thing we define was expected value of a gamble, not expected utility. Okay, expected value of gamble is just the average, right, value of x, and that's important. Definition is what we call a gamble is fair if the expected value of the gamble is 0. Okay, and we call the gamble is not fair, then it's unfair. No, it's mathematics, right? People call unfair, and it's not fair, right? So that's simple. I don't have anything to say except this is the standard way math people write things, right? You have to define everything, right? It's unfair, it's not fair. Okay. So the second one actually goes to the idea that motivate actually what we call expected utility theory, right? So although we have expected utility theory, and that is not something that come from nowhere, actually come from the old thing about St. Peter's bird paradox. What it said is people actually are not willing to participate in fair lottery. Okay, not consider this case. Okay, you would flip a coin. Okay, and if whenever the coin is ahead, we stop the game. Okay, and if I have head, okay, then you get $1. Okay, so if the first one, so put it this way. Maybe this is easier to write down what you get. Okay, so if the first one is head, okay, you get $2. If you have tail and head, then you have $2, you have $4. If you have tail, head, you have 2 to the 3, okay, so on and so forth. Okay, is that clear? So basically, just start from here. You have head and tail, and then go on and go on. Right? You get $2 here. You got $4 here. Right? So on and so forth. Okay. So this is the tree diagram for this guy. Okay. So you can easily, probably if you know, probably some of you may still remember, is what's expected value of this lottery, right? Is infinity. Why? Because you got the first head is half of time you get $2, right? You get this result is 1/4 you get $4, right? And how you get 1/8 you get $8 and so on and so forth. So it's just bunch of one add up, right? You add 1 to infinity, then it's infinity, right? So this lottery, you will get infinity, right? So how are you willing to give me infinity to play this game? Not mention infinity. Are you willing to pay 1 million to play this game? Not even mention that. Are you willing to pay $10 to play this game? Might be. I don't know. How much are you willing to pay? $2? Okay, you're very risk averse. You $2 already, you get $2. Very. Why? $2. You always get $2 minimum. Why $2? $2 already minimum. At least more than 2, right? I mean, yeah. I mean, what? I mean, at least more than 2, right? So I mean, I don't know how much you want to pay, but to me, I think in general, people no more than $8. Okay, and why? Because after $8, right, is 16, right? It's already 1/16. Okay, then actually it's very small, right? The onward probability is very small, right? As we said, sometime when small probability, sometimes people just offset. Forget about it. All right, just basically cut off your mind. Just say, okay, you just think this small probability just becomes 0. Okay, that's actually one of the shortcut in our mind, because we don't do calculation too deep, right? Because I mean, probably you read some psychology or thing is like everyone actually can handle more than 7 objects, right? At most, right? If you have more than 7 items, actually you can't handle, and that means the infinity thing you can't really handle. Maybe you just handle things this up to 7 or 8 outcomes, and for the rest, it just becomes 0. Okay? In that case, that actually will become finite, right? So that's why it must be the case that one of the way to explain why you don't pursue lottery is your utility to high outcome actually is not linear. Okay, so of course there are 2 ways to explain this, right? One way is to put the U of A, okay, it's not a linear one. Okay? A is UA, is not linear. All right, you have to be something non-linear, right? When A get bigger, you flatten out. Okay, and that has a hope that U of this guy actually converge. Okay? This is how. That is the reason sometimes we have utility theorem, right? Expected utility theory is if you have linear, that actually dies. Okay, so that motivate when we have expected utility, you would have a concave utility, right? Because very large amount, you actually value very little, not that much. So that's why when this sum actually is not sum to 1, but sum may increasing smaller, eventually actually converge. Okay, is that clear what we are talking about? Okay, so that actually people talk about this paradox actually like a very universal paradox, because everyone have different view of it. Okay, some people think it's a concave utility. Some people say, okay, this is probability weighting. Okay, some people think other way around. Okay, there are many interpretations of this one. So this is very useful paradox, because everyone has something to say. But anyway, so now that's why we have to say it. If you are risk neutral, which means that your expected utility same as utility of expected value. Okay, so to you, you don't really care about the utility itself. Okay, if I just pay you the expected value of the lottery, you're the same. Okay, you just don't care about, you just simplify the whole lottery by the expected value. Okay, then I pay that amount, then you're the same. Okay, so one thing is like, to you, fair bet, you were happy to do it or don't do it. Okay, and you will not buy insurance. You wouldn't do, if you're fair risk neutral, you don't buy insurance because insurance is unfair. Okay, and also you don't go to casino, also unfair. Okay, and probably you ask this, when we would have this guy risk neutral, and indeed, when we talk about application to big corporation or large bank, we can assume they're risk neutral. Why? Why is the case? Why? One of the reason is, okay, one of the way to justify is the following: is this utility function, right? At the end, you will more or less like not much curvature at the end, right? So flat, not flat, but it's like linear, right? In that sense. So in that case, then it's more risk neutral. If you're a lot of wealth, right, and when it converged, right, and close to that one, right, then that means that it's more linear. Okay, and or you can imagine that if you have a lot of money, right, and actually you will see, right, you have a lot of wealth, and ask you to do lottery, actually you are not so much different, right? So suppose I ask you to do a bet of winning $1 and losing $1, probably don't really, I think it's fair, I think you are okay, right? But I thought about $100, probably you think a little bit more. I thought about 1 million, then you would probably would be risk averse, right? So big company, okay, you can assume risk neutral, okay? That would be the idea. The idea, I mean, law of large number, okay, is the idea that if insurance company do business with many client, right, many customers, and each customer, right, is having the risk, right, and they aggregate the risk, okay, and that means that each risk cancel out, right? So that's why they behave as if they're risk neutral, or they are doing a temporal aggregation, okay, because of I may have lost this year, but next year will have gain, okay. So in aggregate, so they can be risk neutral, okay. So that's why in the modeling of insurance company, you can usually assume they're risk neutral. Same as, I mean, people in finance, right? They know institutional investor, they're more or less risk neutral. You can model in this way. But individual investor, you have to model like risk averse. Okay, I mean, I didn't define risk averse, but that is going to define now. Risk lock and risk averse. If you accept unfair bets, okay, then actually you will be you like the risk, right? Because you value more than the expected utility, external value of the lottery, okay, with nothing, okay. That means that you go to casino or you buy lottery, okay. And risk averse is you actually would be better. I give you the expected value rather than you go to bet, okay. And by St. Petersburg paradox, I think risk averse is the thing that fit most of the application. Okay, and that's why you see most of the model assume risk averse. Right? I think at least I don't see any business application that, except doing the casino industry, they assume risk nothing. Okay, so basically you can safely assume risk averse. Okay, because if people are risk nothing, then probably you should see the you should pay less from equity than bond, right? Because you have to pay people to have a safe haven, right? Safe assets. So, but from finance we know, right? More risk. The fundamental one of the fundamental is risk return trade-off, right? You get more risk, you have to give more expected return to that, right? So that actually comes from the risk aversion, right? Because they have to trade off all that. Okay. Yes. No, I think if I suppose infinity time, but the problem is how do you define infinity? Because okay, how do you pay infinite time is I mean people have finite life. So I mean infinite time is not clear what do you mean, but I mean suppose you're allowed to approximate. Suppose you're allowed to pay many times. Will you change? Will you change? I suppose okay. How many? I suppose I paid 10 times. Would your answer same change or same? Okay. Okay. So, yeah, that can be different. Yeah, because like as I said, right, they're actually the same idea. I said why insurance company can be risk neutral, because you can have a average over across time. They can wait. So then you have a risk lower to you. You think in this way. Okay. I think I partially answered your question, not fully. Okay. So I think it's easy to see why risk averse you have a concave utility. Maybe just draw. It's easy, right? Because of you would prefer. I'm not going to prove because just Jason inequality there. But why is concave? This is I think it's L, right? This is U, right? And you have two outcome L prime, right? And here any so this may be the expected L prime. So this is U of expected L prime, right? And this is P of U L prime. Okay. So this is expected utility. I mean, the red one is expected utility because it's just average of these two, right? This is utility of L, right? And this utility of L. Oh, sorry, I should L double prime. Okay, I sorry the notation. Okay, and I call it L star. Okay, so there's some number, right? Lottery is average of this number. Remember the number, right? And this is when they're concave, right? This is this will be the U of L prime, right? This is U of the whole part, right? So the expected utility is just a linear of this, okay? But the expected value, utility expected value is much higher than this guy when they're concave. Is that clear? Okay, this is, I mean, if you learn principle, this already there. Okay, this is a graph already there. Maybe I should add this graph to, yeah, I should add this graph to the slide. But this is a very standard graph of expected utility. Okay? Just two lottery, right? The expected utility is here, and utility of expected value will be higher. Okay, is that okay? And that's why we subverse as concave, because you prefer give you the expected utility rather than just let the randomness shoot this too. Okay, is that clear? Is that okay? Okay, so maybe I got define in this one. Okay, and maybe I just give a break first. Let a break first, and then we finish this premium later. Okay, just let a break. This premium. Risk preference.就是对啊，你可能会减，因为你就是一期跟两期不一样。 Okay, so still slower than I want to be, but I mean, yeah, but anyway, I try to as fast as I can, but let's see. Okay. So we have risk preference. Okay. So risk loving and risk averse are just a very good way to tell how people behave. Okay. And the more concrete way to talk about this is what we call quantify. It's called risk premium. It's a quantifiable meaning. Okay. So the definition is very simple, and some of you actually told me I'm going too slow, so I try to get faster a bit. Okay. No. Okay. Fast or slow? I don't know. Is it too slow? It's okay. So I keep the current speed. So absolute risk premium, okay, depends on two factors. One is a lottery. One is your wealth. Okay. And the definition is, okay, expected utility with this I don't know what you call it, this lottery plus the wealth will be same as this small u, right? There's no uncertainty here, right? Just like the wealth plus expected utility minus the this one, right? Because why minus? Because you would want to take some, you want to pay some money to pay safe, right? Because like this guy, right? So how do we define an risk premium here? Okay, let me draw it here. Actually, I should have drawn this in the slide, but I think I'm too lazy. Maybe next year I should draw it. Okay. So our lottery, you can have two outcomes, L prime and L double prime. And again, I have L star is here. L star is the expected value, right? And I have this indifference curve, utility curve. Okay. U. Okay. And this is the out utility for L prime. This is utility L double prime. So okay for this one. Okay. And we know if we okay, this will be the expected utility, right? Or use the notation called the big U. Okay, U. Right. Maybe because we care about this. Okay. Okay. Maybe I should be a little bit more careful. Okay. Maybe. Okay. And in that case, it's expected utility. Okay. So what is the risk premium here? Is go to the left-hand side, go down. Okay. The same, you get here the same utility, right? And this is the risk premium. Because you are willing to compare to expected utility, expected lottery, right? You need to pay this guy. Okay. This L star is the L. Okay, you need to pay this minus this guy. Go back to here, right? Because this is just okay. You are willing to accept this much. Okay, so that means how left you can go to make sure that the same as the expected utility. Okay, so that is the thing. Okay. Is that okay? I will try to draw and put it on the slide. Okay, you can see those graphs I try to draw here. I'll try to do that. Okay. Sorry for not having it in the slide. I will do it try to do it during the weekend. Okay. And okay, so indeed, some people would actually in this thing, this is people would call this is certainly equivalent. Okay, it's actually this guy. Okay, it's how much I give you this wealth, you're okay to take it as if you do the lottery. Okay, so if you are risk neutral, the certainty equivalent is just expected lottery, right? So just expected. So the CE will be just when you are risk neutral, this is 0. So certainty equivalent just a wealth plus the expected value of lottery. Is that okay? Is that okay how we define certainty equivalent? Okay, so this is a very standard notation here. Okay. So why we care about this is because of if I know the CE, then I know how they behave, right? Okay, because we just need to, you give me a lottery, okay? I just behave as if I look at the CE, right? So that's why whenever I give a CE, then I'm done. So the next is what we call the relative risk premium, or sometimes look at the textbook they call proportional risk premium. Okay, so there's some change in terminology here. Is your initial wealth is W, and your lottery is L times W. Okay, so it's different. There's a different definition here. Okay, it's not your risk is not taking L, but L times W. Okay, and why you would put in this way is because later you will see how we define. Okay, and it turns out, right, and this you put become the original one, right, and then you just replace the same one. Okay, so this is how we define the relative premium, because you just compare the two equation here, right? You just can see you will replace LW in the original framework, then everything would go the same. Okay, so you will ask why I divide it in this way. Okay, and later you will see why I need this one. This is not very natural. Okay, but there's some reason why we define this way. Okay, and this is you can say this is more like the invention, because we define something later and we back up this guy. Okay, this is where not retro definition, but later you will see why we define this one. Okay, so it's just the fraction of wealth that you are willing to take away. Okay, fraction of wealth take away that to avoid doing this lottery. Okay, you take away this is the fraction, okay, of wealth you are willing to take away to participate this one. Okay, later you will see why we have this one. Okay, and this is not very natural, I would say. Okay, but this is what it means. So so what we're trying to do is because risk premium is actually how people behave, right? Because you would give you the certainty equivalent, you will behave the same, right? So you want to decompose the risk premium actually in two parts. Okay, first is the objective part, which is the variance lottery, right? The more the variance is more risky, right? Because people hate variance, right? The second part is preference. Okay, is subjective part. Okay, and we cover the first risk preference first, and we talk about the riskiness in the second one. Okay. So that is the definition. Okay, we call it arrow pack or sometimes arrow. Is a risk measure of utility. Okay, so what is it measuring? Is we are assuming a concave utility function, right? So how concave it is should be just given by this second derivative, right? The second derivative gives the concavity, right? That is the center thing, right? You can measure things by this guy, right? This is a measure of the numerator will be a good measure, okay? And they propose, okay? Why it's called negative here? Because it's concave, so that's why negative. So put a negative there. That makes a higher of it is a higher risk aversion, okay? Because concave, right? So, and the question is why you would divide the denominator. Why? Why? You want to say something? Okay. And okay, you will be very soon. I explain why you divide the denominator. Okay. But here do note that depend on where, right? Because it depends on where you are. Okay. So let's keep in your mind. I mean, why we need the denominator. But this is what it is first. Okay. And this defined variance, the standard variance is minus mean and square. So I don't think we have to discuss this guy. So now probably justify why we need the denominator is the following. Okay. Turn out to be, we don't prove it, but just we will see is you look at the fair bet. Okay, L. Okay, fair bet means the expected L is 0. That's fair bet. Okay. And if you consider first order Taylor series approximation, which we don't do it next night, but as a result, the absolute risk aversion is just half the variance times this guy. Okay, so that's why risk premium is decomposed in two parts. One part is the objective part, right? It is independent of your preference. Nothing related to your preference. Just how variation of the lottery. The second part is related to how concavity you do. Okay? Turn out to be, it doesn't only depend on concavity, but also care about your slope. At that point, and this is why we have CA, RA, CA. Okay, so that explains why we cover risk. How you cover risk? How you measure your risk at the margin, right? Approximation, right? Because first order Taylor approximation look at the margin, right? So basically, just like look at this curve, right? How can we come up with the lottery, right? Look at let me draw here because I think now we need a fair bet, right? So the same graph here. Okay? I have outcome L prime and L double prime. Okay, it's a fair bet. So suppose equal likely is here. Okay. Okay. Maybe I have well plus this guy. It's a fair bet, so just saying. I do this. W plus L. Okay. And this lottery has two outcomes. L and L prime. Okay. Because fair bet is in the middle. Is that clear? Because yeah, it's this guy. L, which is this is 0. Or anyway, just this plus this guy is actually 0. Okay. So focus on this kind of bet. Okay. And you had an indifference curve here. No, sorry, utility function here. Okay. And what it means is, okay. Sorry. and you have this, right? Your expected is here, right? And go to here. This is your CE, right? And this is your risk premium, right? And what this said is this premium can be decomposed in two parts, right? First part is look at the variance, right? If this more separate, right? You can imagine easily what's then this guy, right, more separate, right? And this will be larger. Okay, I think you can see. Yeah. Yeah. Yeah, good. That's what I'm going to talk about. So RA in this graph is, look at this one, is how this is the slope and how the change of slope. So are they, no, this the tendency of this guy. So look at how this shape, and if you have, I don't know, more curve, right? Then this guy is high. So this is related to this. No, need not be, because it depend on, can be, I mean, depend can be like this, because concave, right? And because this is independent of lottery, right? Because this do not, this no lottery, this guy lottery. So this is how purely at this level of the wealth, how risky I am. I don't need to don't tell me the lottery. I don't need to know the lottery. Okay. So at this particular point, how risky I am and how fair is it depend on this one. So that's Taylor series approximation. Okay. So that is only the first order. No, arrow is can be. Yeah. Okay. I mean, yeah. I mean, of course, it's negative, it's positive, by definition. Yeah. Because L, because I define L is a R, not R plus. Yeah. I mean, if you want, you can say, I mean, W plus A, W minus B, but yeah, if you want to do that. But just being lazy. Sorry for very lousy notation, but maybe I would draw a better one when I update on the slide. So I would just I try to draw a better one. But you can see, turn out to be, that is why we need this guy. So, I mean, that is the reason why they call this absolute risk aversion. It's because they derive from here, right? They derive the first, I mean, the proof is like this, but I'm not going to do the proof. But the proof is like you take a Taylor's approximation and take out the higher term and equate, and turn out to be this is the guy. Okay, but I'm not going to do the proof. I think everyone can do it if enough patience. Okay, so and the second one is turn out to be actually is idea that we mentioned banks or government or big corporation. Actually, your risk preference actually kind of related to your wealth. Okay, look, it's not independent, right? Look at this one. It's like, look at the aversion, right? Here is like the really not related to wealth that much, right? So there's an alternative definition. You take W, okay? And I explain why this is correlative. It's because of if you decompose it in the relative one, okay? That is how you decompose the two. Okay, I'm not going into the detail, okay? But that is the idea, okay? And I guess for people who are not doing finance, you can forget about the relative idea. Maybe next year I take away the relative thing, because I think you create more confusion than it gains. I mean, so probably in the future, I will take away this particular slide, because I don't think you gain learning another way to measure. Okay, I mean, for your purpose, I think this is sufficient for our purpose. I think maybe something would yeah, there's some reason you want to focus, because there's some utility function that assume constant of this guy, and there's some utility function assume there's some reason why we focus on this, because there's some utility form that you assume for satisfy a constant relative risk aversion, and there's sometimes they would assume the model you have a constant absolute risk aversion. So that is the reason why I keep these two, because sometimes you see in the literature when you assume the utility is like this, it's always constant. So that's the reason. Okay. So let me finish the last two. Maybe I can left this to the next class, will be fine. But some question? So is that okay so far? So we cover a little bit fast, sorry. We cover how we start with uncertainty without lottery, right? We learn one way to model behavior is called expected utility. If you believe that you satisfy the 5 axiom, okay, that's what you have. If you don't have the 5 axiom, then you have other way to do it. And the next about risk preference is in the sense that we fix the lottery, right? And we try to see fix some lottery, and then why you prefer one over the other, right? And you would be, that's why we have risk preference, we have risk neutral, risk averse, risk loving, and also we have risk premium, right? And then risk premium, as you can see, is actually coming from 2 parts. If you look at first order approximation, is how risky the lottery is, right? And also your risk preference, okay? And now we just look at compare lottery, okay? The idea is we try to see if we can rank lottery without in a robust way, in a sense that is for a fixed class of preference, how you can compare. So basically the following, okay, is can we have a lottery, okay? You can say one lottery A better than lottery B, regardless of your preference, okay? Regardless of which attitude, okay? The idea is following, okay? As we are focused on FOSD, first order stochastic dominant is we assume people like more money than less, okay? I think this assumption is fine, okay? And in that case is if we like more money than less, okay? And can we say, I give you 2 lottery, okay? You always prefer one or the other, regardless of risk preference. That's called FOSD. The idea is that definition is, okay, looks a little bit crazy, okay? If it's this integration better than this integration, okay? So what does that mean? Okay, looks amazingly crazy. But let's look at the alternative one. That's usually you see. Okay, do note that this is crazy is because I'm asking for every U. Okay, look at again. Is difficult to check is because for every lottery, I need my expected is higher than this one. All right, so regards to U can be risk neutral, can be risk averse. How can you check this guy, right? This is a definition, right? Let me repeat the idea. FOSD is asking, regardless of your risk preference. As long as you like more money than less, your expected utility under the lottery F is better than under lottery G. Okay, so no way to check this guy, right? So how can you operationalize this? It's turned out to be this is same as this guy. Okay, Fx is less than Gx. Okay, what does that mean? That is actually very simple. Okay, because F and G are just CDF, right? Cumulative distribution function. Okay, this is X. Okay, and to be simple, I assume X start from 0. Okay, so X is a lottery. It start from 0. Anyway, I don't need this one anyway. What is this FOSD means is the following. This is the F and G, right? And it must be 1 and 0, right? Because it's CDF, right? Cumulative distribution function, right? Because F of X is probability that X is less than X. Okay, G the same. Okay. So what is the F means is this one is the following. F is better than G means if F is like this, okay, G have to be at any point of time, G must be higher. Okay, so at any point, look at any point, G must above, so something like this. So means G is left of F. Okay, whenever G is left of F, okay, then F is better. Why? Because F always getting, you're always having more probability of getting more money because it's less than or equal to, right? So for it's more likely that you get higher money. Okay, because as we said, we prefer more to less, right? So we have to say you always get more money, right? In terms of probability. So you would say F is better than G. Okay, so it's pretty restrictive, right? Because you need to have at any point of time, okay, all right, it's more likely to get more money under F. Is that okay? Because because the probability is like here, right? So it's more probability on the right hand side than left hand side. Is that clear? Right? Because you get this, right? It's like the increment, right? So it's just like more likely that you get, yeah. Okay. Oh yeah, yeah. I don't know how to draw, but yeah, but you, yeah, how to draw it? You draw a PDF, then something like, okay, something like this. This is yeah, no, but need not be Bell, right? But can be anything. This need not be Bell. So this can be exponential also fine. So that's why it's hard to exactly why, I mean, there's no one graph can present this, but this is just because the difference says the probability of this, right? It's just the difference between this, right? So it's more likely the probability is more weighted on this side. Okay, so that is for no matter which point you're looking at, it's more likely on the more number. Okay. So the next one, okay, it's called SOSD. Okay. So the first one is pretty restrictive. Okay. Turn out to be you can see almost very unlikely you will see FOSD. Okay. And that's why we look at another one. It's called SOSD. Okay. A second order stochastic dominance. The idea is very simple. Okay. It's the following. This guy, the same. This is same as FOSD, right? The change is we focus on concave function. So focus on concave means we focus on a risk averse, right? For all risk averse function, okay? And further, this is not enough. We have to put one more restriction. We put in that the two lottery give you same expected yield value, okay? And is that okay? The two requirement. First, we restrict only to same utility. Second requirement, they are the same expected value. Yes, your question? Okay, so this is two restriction, okay? And you may ask, okay, why restrict these two, okay? The reason is, if you don't restrict these two, actually you can't really compare, okay? Because we have to compare for every non-decreasing concave, okay? So that is very strong. But turn out to be, it's very simple, okay? Turn out to be, okay? You can simplify to this. What does that mean? It means the following. Okay. It only mean this. Okay. I compare the two. So I need not require all the time G is left of F. If they do, then already yes. Okay. Because later we will show FOSD, we imply SOSD because you can easily see by definition, right? Because, right? So what we now require is the following. So suppose I have start with an F. Okay. So what we actually need is this is still fine. Still fine. Okay. This is still fine as long as look at the area. Okay. At any point of time, look at this area. This area for F. This area for G. Area for F is less than area of G. When you keep moving, even the intercept, the kilometer area from F is less than G. Okay, so let's look. The idea is area up to any point of F is less than G. Okay, so that is what it means. Okay, and if that is the case, then yes. And so this one is still looks like sometimes they could check. Okay, it's not easy to check. Okay, but I should write that down here. But there's a easier way to see is this one. Okay, if we have the variance under F is less than variance under G, okay, we're done. Okay, this actually implies SOSD. Okay, I mean, of course, we have expected X. Okay, if this is the thing usually you would do, is the same mean under F the variance is smaller than G, then this is the SOSD. Okay, that is also what we call mean preserving spread. You will see in the textbook or in the book. It's like they have same mean, but the variance is higher. Of course, you would prefer the one is less variance. Okay, this implies this guy. Actually, you can prove it. Yes. Not easy. because they're the same. Actually, they have same mean, right? And then the variance small. Okay, if the same mean, because the same mean, right? The variance like more spread out. So if they, yeah, you can. Probably you can look at the same mean here, and look at this side, right? Then if they more spread out, right? If there's more like this, yeah, then you'll be higher. I mean, it's hard to write a good. That's why you don't see in a book, right? That's usually seen in a book. Okay, but it's easy, right? So this often you can see, right? That's why, in some sense, that's why you look at later you will see people focus on mean and variance, right? Because they have same mean, you hate variance if you're risk averse, right? Actually, there's nothing new here, right? And that is that's somewhat related to this idea, right? The risk. We have this part, right? But anyway, I guess I should end here. Although we can't finish, but we almost finished. I think it's okay. So slightly behind, but I try my best. I mean, to balance the material cover and the speed. But let me know if I'm still going too fast or doing a little bit too quick. So I see you next Friday. So have a nice weekend.